So would like to introduce Northern Ireland slightly. So Northern Ireland is part of the UK. So UK has four key regions. So North Belfast is the capital of Northern Ireland, and then okay. So but we have quite a specific location. It's because Northern Ireland was used to be part of the island. So in Northern Ireland, the Giant Causeway is really famous, and yeah, if you have chance, welcome to visit Northern Ireland. So I think this background, we all kind of agree that the human activities, the industrial activities recently caused the significant amount of CO2 emissions, and these also bring the challenges of climate change and global warming. And so I think we need to make the actions and to reduce the CO2 emissions. Basically, I think the final objective aim is to reduce the CO2 concentration in the atmosphere, because this concentration is going up. So, but the point is we can use renewable energy, hydrogen, bioenergy, or carbon-free energy source, but the fossil fuel-based energies or fuels, we still have to use that. So we can't. It could be phased away gradually, but we still need to use it. So then we have a lot of CO2 comes out of the using of the fossil fuels, and then we need to remove it, and we can store it or utilize it. So that actually is very important, not to combat climate change issues, but it will have significant impact on the industrial or economic activities. So there are different ways to reduce CO2 emissions. Like we change our habit to save the energy, even the food waste. Reduce the food waste. There are so many ways to reduce it. So, but in terms of the CO2 carbon capture itself, we need to remove carbon directly from different sources. Sorry, I might just fit this. Sorry, I just want to stop the noise. Okay. So we have this. I think we know there's mainly three key categories for carbon capture. So we have pre-combustion, oxide combustion, and post-combustion. But probably we need maybe new terms, or because the pre-combustion mainly relate to the CO2 removal from the syngas. Because syngas come from the carbon-based feedstock, we want to remove the carbon and produce hydrogen, and then hydrogen utilization is only generate water. But recently we also, but the technologies like to remove carbon dioxide from syngas is really simple and similar to the technologies like for post-combustion CO2 capture technologies. Like the CO2 capture from the syngas, it's quite similar, could be to the capture from the flue gas. So, but anyway, there's three key categories: pre-combustion, oxide combustion, and post-combustion. So I think traditionally, most of us, I think we are talking about a post-combustion CO2 capture, and that is really the key area to remove the CO2. So for post-combustion CO2 capture, we have, I think there are three key categories, three key areas. The first one is CO2 absorption using liquid solutions like amine or ammonium, or even alkaline solutions. And for that is liquid side, I think there's significant amount of activities. Professor Peter Zarin mentioned, and also we have a lot of talks about the CO2 absorption. And again, CO2 absorption using solid is another key area. And I think in general, there's more commercial activities about CO2 absorption using liquid, but the CO2 absorption using solid is promising in terms of the energy efficiency. So for CO2 absorption, we also have key three categories. So that from our perspective, it can be divided into low temperature, medium temperature, and high temperature CO2 adsorption, and that based on the solvent. So like MOF-based materials, polymers, zeolite, even biochar, and there's a lot of research activities there, so they can be used for CO2 adsorption at lower temperatures, relatively around room temperature. So medium temperature, I think, is around 350 or 400. I think one of the best candidates for medium temperature CO2 adsorption is magnesium oxide. It has really high theoretical capacity, like I think it's over 20 millimole per gram. But the problem is magnesium oxide is really basically it's not working in reality. So it has very low kinetics, and it might, because of the surface, the crystal surface, or because of the formation of the formation of the magnesium carbonate on the surface to stop the diffusion of CO2. For CO2 adsorption at high temperature, I think calcium oxide is the best one, not just one of the best. I think that calcium oxide is the best adsorbent for CO2 capture at high temperature. There are so many activities to develop new materials for CO2 adsorption. I think the honestly, are we going to introduce integrated CO2 capture utilization? I think that's another kind of a direction to solve some of the CO2 absorption challenges. There's a lot of activities, I think, in the past 20 years or even earlier. But again, I think in a certain period, the research activity kind of reduced because of the challenges. A lot of work have been done. But again, I think recently, because of new technology available, so it become more popular again. So I think the third key area of CO2 capture is membrane-based CO2 capture or separation, because it's really a lot of researchers in that area, and also membrane has been traditionally used for the separation of other gases. So it's very, I think, easier to transfer from the separation of other gas to the CO2. So a lot of activities. I think personally, these three areas are the key areas of post-combustion CO2 capture. But again, of course, we have other cryogenic process or other process. Like today we heard about supersonic CO2 removal. That's another emerging technology for CO2 separation. Other technologies, I put the direct air capture deck here because it can be used for both pre-combustion. It's not, the CO2 does not just come from the post-combustion, it comes from also other activities. So deck, I think maybe my personal view, I think is the fourth key area. So it's after the CO2 absorption, membrane separation, and other deck. Deck is really important. And carbon mineralization also very interesting area. I have talked to a few researchers in the work in that area. So I think this picture probably come from the Professor Peter Saring's previous work. And so one big question is, okay, what are we going to do with the capture CO2? Personally, I prefer this route, so CO2 utilization, but I don't against the CO2 storage route. I think each technology should play its role in future. So we should the technology should complement each other. So because all the development of each technology, it depends on the scenarios. So the location, the policy behind it, and the technology behind it, even the other the plant or manufacturer. For example, there's a manufacturer plant that have a lot of hydrogen, so probably the CO2 hydrogenation will be good option. Or there's a really nice location that have the caves which can be used for CO2 storage. So I think there are different CO2 storage and CO2 utilization should play their own role in the future. But no matter CO2 utilization or storage, the CO2 need to be captured first. So CO2 capture is a process to purify or to get a high concentration of carbon dioxide. So conventionally, I think that's for CCU is basically you need to capture CO2 and we need to regenerate the solvent. And then after that, we need to do the CO2 utilization. So basically, at least there's 3 steps or 3 reactors. At least there's three reactors. So I think in many cases, more units will be involved for the conventional CCU. We know many challenges, like challenge for CO2 absorption using liquid. And one of the challenges is you need the solvent regeneration need a lot of energy to heat the water and then the cool the water. So a lot of energy wasted. And so that's 3 stages, at least 3 stages. But so recently, a new concept comes out. We are one of the, I think we are one of the pioneers in this technology development. So we call it integrated CO2 capture utilization. We also have colleagues or friends call it integrated CO2 capture and conversion, so ICC or ICCC. So internationally, most of us use ICCU term. So in this technology, we have just one reactor. Instead of 3 or 4 reactors, we just have one reactor. And we introduce CO2 source, different syngas or flue gas. So the materials will capture CO2. So, and then we call the dual function material has 2 functions. First function is to capture CO2. Then when the materials are saturated for CO2 capture, so we stop the CO2 flow and we introduce a reducing agent. It can be hydrogen or methane. So the hydrogen, for example, will be introduced and react with the captured CO2. Simultaneously, the solvent will be regenerated. So in this case, the solvent regeneration can happen at the same temperature as CO2 capture. So I think that's quite significant from some perspective. For example, for calcium looping or for solvent regeneration, we spend a lot of time now to reduce the energy for solvent regeneration, no matter it's liquid or solid. But in this case, we don't need to increase the temperature for solvent regeneration. It's just single temperature, so fixed bed is possible. This morning, Professor Fang also mentioned the attrition issues of the solid for CO2 capture because there's a freeze-ice bed recycling reactor. So cycling reactor, you need to transfer the material from one reactor to another, and attrition is an issue. But in this case, just fixed bed can be used. So the material is static, just stays there. So I think that's one of the advantages. And of course, bring the temperature down, like calcium looping or calcium oxide-based CO2 capture. And traditionally, the issue is for calcium looping is the regeneration of calcium oxide need to happen at 800 or 900 degrees C. At that high temperature, the material sintering is a big issue. In this case, using this ICCU concept, basically the regeneration temperature just can be brought down to 600 degrees C. Basically, the material can be very stable because we avoid the high temperature. And so that's bring the temperature down. Then, of course, it will eliminate the energy requirement for some I think I'm not sure how many percentage, but I think definitely bring the temperature down, it will reduce the energy requirement. And then transportation issues will be avoided, and the attrition issues are also avoided. And I also want to highlight from the chemistry perspective or reaction perspective, because for conventional like CO2 hydrogenation, the CO2 and hydrogen will be mixed and converted to different chemicals or fuels. And commercially, the more ratio between hydrogen and carbon dioxide is about 5:1 or 4:1. So because of this hydrogen to CO2 more ratio, thermodynamically, it will limit the conversion of CO2. For example, for reverse wet gas shift reaction, the maximum conversion of CO2 is about 65%. So if you check the papers published, no matter what kind of catalyst the researchers use, how excellent, the CO2 conversion will be normally less than 65% because thermodynamically it's being limited. And in this case, hydrogen is in gas phase, and CO2, if you use solid, we use solid adsorption, CO2 come from the solid phase. So basically the ratio between hydrogen and CO2, if in the gas phase, is very high. So we don't know how high that is, but basically very high, and that will remove the theoretical limitation. So the conversion can be 100% of conversion of CO2. And we actually experimentally we achieved that, and it's one of the work we are ready to submit. I think we submit to a few journals, but get rejected. We can submit to a new journal. So basically, it can increase the CO2 conversion. So for ICCU applications, a lot of work currently focused on solid-based ICCU. So we use solid, like as I mentioned. So if we have like nickel calcium oxide, so have two functions: the calcium oxide for CO2 capture and nickel for CO2 conversion. But this technology can also be used for liquid-based technology, liquid-based processes. So let's say for amine scrubbing, amine solution-based CO2 capture, we understand the capture is around, let's say, 80 degrees C. The regeneration is 120 degrees C. Just an example. So if we can use this ICCU technology, so during the CO2 during the solvent regeneration stage, we don't increase the temperature. So that means we don't even need to transfer the liquid. The liquid can stay there, and then you introduce a reducing agent. So for liquid reactions, the reducing agent will, after CO2 capture, introducing a reducing agent that can react with captured CO2 within the amine solution. But then you definitely need to add some catalyst into the amine solution, and the reducing agent will react with the CO2, and I think it will be a homogeneous catalysis. Then the product will be produced, and then after the captured CO2 converted, you can introduce flue gas. So in that case, we don't need to basically we don't need two columns for this process. The one column to avoid the heating up of the amine solution. We know that is a big problem because there's significant amount of water inside. But I think I only see a few papers published JAX or SES catalysis about this concept. So it's still early stage and quite low TRL at the moment. But I think very, very interesting. But then there's a lot of work about solid-based ICCU. So, and most of them are focused on the medium, high temperature solid-based ICCU. So like high temperature is calcium oxide based, or other solvent based. Medium temperature is magnesium oxide based. Low temperature like MOF, zeolite, CTF. The issue is for ICCU, we know there are two functions. You have CO2 capture function, have the CO2 utilization function. So that means it's easy to find a catalyst to convert CO2, capture CO2 to fuels and chemicals at medium and high temperature. So we know there's many reactions, CO2 hydrogenation reactions happens at medium and high temperatures. But for CO2 utilization at low temperatures, you will need like photocatalysis, electrochemical catalysis, and or non-thermal plasma assisted catalysis. So you need a specific knowledge about the photocatalysis and non-thermal plasma catalysis. That can, but then I think that is possible, but they're just, I think I don't see any paper in that, maybe just one or two papers in that area. So basically you need to find a low temperature at the solvent, and then the catalyst working at low temperature. So because we need to match these two temperatures, that is mentioned here. So research challenges of ICCU. So we need to find the right solvent, right catalyst, and how we can mix these catalysts, how we going to combine the catalytic side and the absorption side together. So a lot can be done. So this side can be combined at a molecular level, or the particle scale. So, and also the temperature. So the capture temperature and also conversion temperature. It is noted that we highlight the ICCU working at one temperature, but in reality, the ICCU can happen at two different temperatures. And so what kind of reducing agent are you going to use? So hydrogen, methane are quite common reducing agent for ICCU using solid dual function materials. But if using liquid amine properly, I think other reducing agent can be used. So it's a lot of chemistry will be involved. So what's the product? So carbon monoxide, and that's my focus. So we can produce methane, so it's ICCU methanation, or other products like high pressure. So ICCU for methanol production, I think it's promising. Personally, I don't see any paper in that area. Probably some groups already working in that area. So some statics, I think maybe it's a little bit outdated, but that's our best guess. So it's about 150 journal publications in that area, become quite popular from 2014. So three key areas, I'm going to also mention that later. So ICCO, reverse organic reaction, ICCO, so that should be DRM, dry methane reforming, and ICCO methanation. So some nice papers like Science Advance, Nature, EES, Apply B, and a lot of papers in CEJ at the moment. So many unknowns gain increasing interest, and I think many research groups there are more and more research groups in this area. So these are two nice review papers about ICCO. So as we mentioned, this is from paper from actually from Dr. Zhou Hui published in CCST. So it's ICCO, we have like methanation route. So we capture CO2 and using hydrogen convert the CO2 to methane. I think this route has its specific importance. Like in some certain areas, they have the natural gas and the CO2 is in the natural gas. They can remove the CO2, then they add hydrogen, and because natural gas has a very good infrastructure, then ICCO can also be linked to reverse water gas reaction, which is CO2 hydrogenation to CO and water. Or ICCO can be integrated with the dry reforming reaction. So basically, with the reducing agent is methane instead of hydrogen. So producing syngas, it can be then converted to different high-value chemicals or fuels. So I probably in this presentation, I want to focus a little bit on the ICCO reverse water gas shift reaction. So it's more specific now. So this is also publishing this review paper. And so a few examples. So normally we have two functions, have the catalyst nickel-based, iron-based, or platinum noble metal-based. Personally, I don't agree with this using noble-based, noble metal-based dual function materials, because unlike conventional CO2 utilization, the catalyst will only used for clean CO2 and hydrogen. In this case, these dual function materials will be used for flue gas, very dirty flue gas. So I think this noble metals probably will have issues, when they are used in the flue gas. But anyway, there's some research there, but I think it probably can be used for some specific reasons. So. Okay, so we have done some work in this area, ICCO, reverse water gas reaction. At the earliest time, we use nickel and calcium oxide, two functions, and 5% hydrogen for the reduction. So clearly, during the carbon capture stage, you can see the CO2 can be captured. Then this was done in a tubular reactor. So we use nitrogen to purge the CO2. Then as soon as we introduce carbon monoxide, introduce hydrogen, this blue line, then we can produce carbon monoxide. But the reaction time is about 50 minutes at that time. So we introduced the cerium there to increase the performance of this material. So basically, it's quite clear as soon as we introduce cerium, the distribution of nickel particles becomes much better, and that actually enhanced the performance of the material. So the first one, the material is deactivated. The second, we introducing cerium, the material is quite stable. So basically here we just switch between hydrogen, CO2, hydrogen, CO2, hydrogen, CO2. The 20 cycles here. So the kinetics, I think the kinetics is really important. As we said, we need 50 minutes to complete this CO2 utilization stage. But if we increase the temperature, then it can go just 10 or 10 minutes to complete the CO2 utilization. I think that is one of the reaction research direction. That's basically what is happening in our research group. We want to reduce temperature for ICCO. That's also one of the questions I asked one of our friends. They work in this area. So I think this is a research direction. We want to reduce temperature. Even now, we reduce the solvent regeneration temperature, but for the high temperature one, like calcium oxide based, the temperature is still quite high. It's about 650 or 600. So we talked to the companies, they want much lower temperature. So this is about particle size distribution. I think due to time limit, I will quickly go through some of the existing published work. And if you're interested, you can send us email, can have further discussion. So this paper is about the distance between the active sites. And I think that's important because during CO2 capture, the volume of CO2 will increase. So that means calcium carbonate. Sometimes the formation of calcium carbonate can encapsulate the nickel particles, and we basically confirmed that. So there should be a certain distance between nickel and calcium oxide, but I think the distance should be not too big. Otherwise, the synergies between these two active sites will be quite poor. So we also investigate the influence of the support of this material. At that time, I think our knowledge kind of strength are limited by the dual function material. So we always thought, okay, we need two functions, we need the catalyst, we need the solvent. So that's why we try to enhance the performance of this. But again, I think we need to know why we are doing this. So why we are investigating different support. The purpose, I think, it should be increase the kinetics. Like in this case, you can hear clearly. Increase the temperature, the reaction time, shortened significantly. But could we reduce this reaction temperature by manipulating the materials or catalyst? So that's cycles, and so we also have these concepts. So dual chemical calcium chemical dual looping. So basically, you have chemical looping and calcium looping all happen together. I think the purpose again is try to increase the conversion of CO2, increase the CO2 capture capacity, and also to basically to reduce. I think for this work we haven't investigated reduce the temperature. So one of the outcomes of this is nickel-based catalyst is difficult to be reduced during the CO2 hydrogenation stage. That's why in the CO2 capture stage, you don't have carbon monoxide produced. But for iron-based catalyst, you have the carbon monoxide produced. That could be problematic if we are capturing CO2 from the flue gas, because they don't want to generate new pollutant, CO, in the flue gas. So basically, that it will be a kind of engineering issue if we are using iron-based dual function materials for CO2 capture from the flue gas. So probably you need to add manipulate or modify the dual function materials, or probably use air purge to oxidize the catalyst before doing the CO2 capture. So this is I really want to highlight this work because I think it's quite interesting. It's the first paper of CCST. So for reverse Water-gas reaction, it normally need a catalyst, and that's why everyone, I think, will use a catalyst for reverse Water-gas reaction. But in this work, we just one day just say, okay, why not we just try calcium oxide, see whether just calcium oxide without any catalyst. So we can and the results quite good. You can see calcium oxide only can capture a lot of CO2 and can generate about 4 or 5 millimole per gram of the carbon monoxide. And the conversion of CO2 is about 75 or 80%. Remember, for conventional reverse Water-gas reaction, it can't go over 65%. So in this case, it's already better than conventional process from the perspective of CO2 conversion. But of course, it's different technology. This one is switching the gas, not by looping the material. So we did some work, and basically, the ICCU, I think the advantage is it's quite stable as this because we bring down the temperature. Although for this one, initially have some deactivation, but it becomes quite stable later. It's about 3 or 4 millimole per gram. If you are working in the area of solvent-based CO2 capture, like especially low temperature, you will know higher than 2 millimole per gram, it will be quite good solvent. So MOF-based materials normally just have around 1 millimole per gram. Also, a lot of work just get to the CO2 capture capacity from the pure CO2 experiment. So we also tried the marble stone, very simple material, just a stone. And the results are also amazing. So we have, you can see here, we have about 10 millimole per gram of CO2 CO production. So that's quite significant. And the conversion is about 85% of CO2 converted to CO2. And this is actually quite good. One of the work is not I didn't present here is we achieved nearly 100% of CO2 conversion. But we talked to a company. They said, okay, you don't need 100% of conversion of CO2. This is quite good because the mixture of CO, hydrogen, and a little bit of CO2 is not a problem for downstream utilization for aviation fuel production. So I think this can be used, directly. So I want to highlight this ScienceShare website because I spent a lot of time to put articles. They also have first category, second category, third category, and fourth category. So for ICCU, then first category, then we have second category, we have ICCU introduction, methanation, dry reforming. So then third category, fourth. So for the early learners, it will be a very nice website to get some knowledge about. So we save your time for literature review. And this conference, CCS 2023, is an annual conference for carbon capture science and technology, which was launched in 2021, I think. Last year we have the first annual conference. It's the second time. We don't have the impact factor yet, but we have the site score now. So it's about 7.2 in June. I think this month we expect to have a site score around 10 at the end of the year. We also expect to have the impact factor soon. This also, I think, I'm quite happy with the quality of papers published in CCST because it's very nice papers and it's all really related about carbon capture. So we really think this journal could be a core journal to publish carbon capture related papers. So another a platform I want to promote is International Association of Carbon Capture. It's also based on the it's linked to CCST, but it's independent of CCST, and we have some friends or colleagues working together to promote carbon capture. It just get registered. I think get registered. Some here we have the charity number. We got it last week. So it's Northern Ireland registered charity now. So we have many distinguished fellows and senior members. So for distinguished fellow and fellow which are invited, senior member, you can submit your application anytime. We're going to have many activities for the IACC. So I think most of them will be free, like training, or we also have some awards available. So this, if you are interested to join us, can just scan this QR code. And so also, I think for this platform, we are also a little special because I think all of us are early career, middle career based researchers. So we really, I think if you are really interested in carbon capture, join us. You can send us email. And if you have the passion, we can work together. We can work together to promote the carbon capture. And also, I think it should be good for the career development, especially for early career researchers like PhD or postdoctoral researchers. So in conclusion, I think I want to promote ICCO, and it can be used for liquid-based amine solution CO2 capture or solid-based CO2 capture. For solid-based CO2 capture, it also can be divided into an ICCO reverse water gas reaction, ICCO DRM, ICCO methanation, and also other ICCO technologies. I think there are some activities, commercial activities also I have not mentioned. So hopefully this technology can be commercialized soon. And of course, there's a lot can be done, so like fundamental research. So I would like to thank to the collaborators, and many students' names are missing here, and also EU funding support. Okay, thank you very much.